So here all you see is total weighted average based on all the 5 assignments and the 2 midterms. So weightage of about 60%. So still there's 40% out there. And then I just ranked it and indicated roughly how I will go about assigning grades, so that you don't panic just because you have a mark of 50% doesn't mean that you're going to fail this course. Okay? And it is on Moodle, and I uploaded it only this morning. I noticed that many of you have been trying to get at the current standing on Moodle. I was impressed. Someone was trying to log in at 2 o'clock in the morning last night. But I finished marking earlier, but I didn't do that weighted calculation. So I just finished this morning. And once you get your marks, you will know what your mark is. There are no duplicate marks, so it's all unique. You should be able to find out where you are in the class. And that's what is important, particularly for those at the bottom. It is important that you do put some additional effort in this course to move it up. The average for the midterm, second midterm itself, came to about 52 or so, and the highest was 78. And if I follow this kind of a grading, then I will get a class grade point average of about 2.9. I'm comfortable with about 3.1 or something like that. So I hope that the people in the bottom that I have assigned D to 2, if I change that to C, you must give me a reason why I should do that. And then it will bring it up to about 3 or so for the class average. Okay. And remember, still 40% is out there, and still a few assignments are there as well. Okay. I think there's one assignment that you should return by this Friday, and hopefully there will be probably 2 more assignments before the end of the term. So that's just your standing. Any questions on that? Yeah?
The potential grade is up if you match the average of the grade, or is that potentially
if you maintain your relative ranking, everything depends on the relative ranking, right? So a person who is an A and says, oh, I've got it made, and then doesn't do well in the final, can slip back. Okay? Whereas a person in C could work hard, 40% is still a large number. And particularly, I think you're not able to see it here because of the color, but the way that I pick the break points where I assign is to look for fairly large differences, okay, in the marks. So, for example, if we had a plus-minus system, I would have given the top person A plus, 89. The next one is 80. So there's a big difference between 89 and 80. But if you look at 80.3, 80, 79.7, 79.6, something like that, they're a cluster of 4 people together, okay? And I grouped everything into A. And then after 79, there is a big gap. The next one I find is 74. Okay? So B starts there and goes down to 65. And between 65 and 57, there is a big gap also. So I said, okay, I'm going to cut off there. So that's the kind of logic that I will use in deciding the breakpoint. So there is really no fixed mark that says that if you get above that, you're going to get A, because this is not a standardized test. The test is to both challenge you, make you learn, at the same time get me a good distribution, a good ranking. And I'm quite happy that there's a good distribution. And looking at the exam also, I felt comfortable. I don't feel that you're totally lost. There are a few people who are totally lost, but for most people it is lack of time. But the other thing that I noticed, and this is something that I've learned, I will never do again, is give you a practice problem set. Because you interpret the practice problem set completely wrong from the way that I expect. For me, a practice problem set is one that I will practice on, okay, after I've studied all the material. I think the way some of you took that is, I'm going to focus only on the context. I'm not going to study anything else, right? that is not the intent of a practice problem set. So I will refrain from giving anything like that in the final exam because everything that we covered in the course should be included in such an exam. I actually felt very proud after I made the exam because I thought the exam was nicely covering many aspects in this course. The relationship between the linear problem and the nonlinear problem, the equivalence between a higher order system and a first order system, linearization. So I wanted you to see the whole kind of forest, and there are some comments that we are lost, okay, and that exam, if you're done fully, and that's one of the points of asking you to do it as an assignment, is to see the interrelationship between eigenvalues of a matrix and the characteristic roots of a higher order differential equation. So the equivalence between a higher order and a system of first order equations. I have a suggestion for you. Would you mind a quiz on the same topic? Now I will focus the topic. Everything that we did, you've already done it in an exam, like a midterm exam. You're doing it in your current assignment. But in addition, a quiz with writing on a problem will be different, but the same ideas, testing on the same ideas. Because I think it is important that all of you get that connection between various aspects that we're seeing in this course. And that I feel some are missing that part. So I just thought about it after marking it. Now, is there any strong objection to? It's an entitled class. Because if you have to do that, in that exam you didn't find the time, right? So I want you to do all of them, except I will drop the second question. Okay. So not on the equivalence of a block diagram representation, but everything that was in the first problem will be there with a different problem, so that you get the idea of going through the motion. Particularly, I guess it's simply because we didn't study that part, equivalence between the higher order and first order. Many people have difficulty there. And doing it for a linear problem, putting it in the matrix form, and for a nonlinear problem, doing it as a set of equations, and then linearization. Yeah. So you're good. That's fine. Any day is fine. You should. No, it's not a vote. Everybody has to agree. If you don't, I'm not disappointed, but I think we lose an opportunity to reinforce that part. And I think you probably have a good idea. You are in the top of the class, so it doesn't matter to you, right? Why subject yourself to another torture? Monday? Okay. Thank you. So I will prepare a quiz along the same line, just to reinforce those aspects. Okay, any other questions or comments? Okay, if not, let's continue, and we still have quite a number of topics to cover, but we are focusing primarily on feedback control systems. So what I'm going to do is look at feedback control systems for two types of problems that we've talked about. So we're going to use examples. And what you should be able to do in the final exam, and then since you go out into industry, is use these concepts. Replace the heated tank as just an example with any other process. Okay? And then design a controller, understand what various functions in the controller, like the proportional, integral, derivative, what do they do to the process. And we're going to do that through a series of examples. In the last class we looked at, and we should be able to do it by Simulink, by MATLAB programming, and by hand. Okay? By hand I'm insisting simply because it's the only way I can test you in the final exam. Okay? But otherwise these days, hand is not really necessary because we have these tools. But you need to understand the tools, and you should be able to use those tools. Okay, so we looked at regulatory problem. Okay, that is, when you make a set point change, you want the process to track that set point change. And the last lecture, almost a week ago, we looked at this problem where we had only a proportional controller. So GC is the proportional controller, and there is the heater for the heater. I guess I probably put the wrong program. Not right. Okay, there. I don't want that now. Okay. So we are looking at only a proportional controller. Okay, there it is. And the heater transfer function is simply a gain 1 over WC. And then the process transfer function is a first order process, 1 over tau s plus 1. Okay? And there is no measurement delay, so in the return cycle, in the feedback loop, there is no delay. It's simply a signal instantly measured. And what we are asked to do was look at the response of a proportional controller for various gains using a set point change of 5 degrees in TR. So this we need to understand, the difference between a set point change in the process, which the process must track, versus a disturbance rejection, a load change. So if I change the inlet temperature, I still want the outlet temperature to be at the same value as before. Whereas when I make a set point change, I want the outlet temperature to follow the set point change. So I want the process temperature to go from 80 to 85 degrees. So I increase this by 5 degrees, then this must track. It must go from 80 to 85 degrees. Whereas if this changes, the disturbance changes, that is the inlet temperature becomes from 40 to 45, you need to adjust your heater duty in such a way that the outlet temperature still is maintained at the old value of 80 degrees. So these are two different kinds of problems. The framework for analysis is the same for either one of them. So here for a set point change of 5 degrees, we did this in the last lecture by Simulink. Okay, so I'm just completing that part without Simulink. Okay, so we have to find the effective transfer function between the outlet and the set point change, T prime and TR prime. So if you look at the process diagram here, so that's going to be the effective transfer function. By looking at this one, is going to be everything between the outlet and the inlet in the forward path. The forward path is this way. Okay, so it's going to be GC times A times 1 over tau s plus 1 divided by the feedback loop, which is everything in the loop. Okay, but in this case there is nothing in the return loop, so it is simply the same thing, GCA divided by tau s plus 1. That is your effective transfer function between T prime and TR prime, the deviation variable between the outlet and the set point change. So if the set point change TR prime goes by 5, the outlet temperature should increase correspondingly by 5 degrees. So the control GC, you should tune the controller GC in such a way that it reaches that target in the best scenario, in the least possible time. Okay. So this is the effective transfer function, and what we have done is we have done some algebraic manipulation to it to write it in the standard form. Okay, and that's what you see here. So this is written as a gain, a new gain, I'm calling it as A1, and a new time constant tau 1, S plus 1. So it's still a first order response for the whole effective transfer function is still a first order. Okay? That is something important to notice, because when I change this from a proportional controller to proportional integral controller, the effective transfer function will change its characteristics from a first order to a second order system. Okay? So this I would request you to go through the algebraic manipulation, take the previous one that I wrote down as an effective transfer function, and plug in all the numbers, and what you're going to get is this as your effective transfer function. Okay? And then we're saying we're making a step change of not 1 degree but 5 degrees, and that's what gives you this. So this is nothing but TR prime in the Laplace domain. If I make a step change of 5 degrees, then the Laplace domain it is 5 over S. So this is then the output, T prime. The output process temperature is 5 over S times that number that you see, 0.2632 divided by this. So this you should be able to do in an exam. Invert it, do partial fractions, invert it, and I keep repeating it. When in an exam, I give myself the freedom to give you up to a second order here. I don't count the 1 over S there. You should be able to factorize a second degree polynomial to get into partial fractions. Okay? And then I'm here using MATLAB to define that output and then take the inverse. And what you get is, in the time domain, the response of the system. Okay? So now we need to plot this to see how the response is. And most importantly, all these numbers will change. Okay? So this number 0.2632 depends on Kc being equal to 5. Kc is 5 that appears in all these places. If I change the gain on the controller, the proportional gain on the controller from 5 to 10, I need to reevaluate all these constants and re-invert this particular transfer function to get the output. So all these numbers will change. The functional form will be the same, but all the numbers will change. Okay, any questions on that? You should be able to do analysis like this in an exam where you get the output response and answer questions like what is the time it takes to reach 80% or 90% of the steady state? How is it affected by changes in Kc? Things like that. Okay. If there are no questions, let me go to the next problem, which is what I call the regulator problem. So here there is a change in the load, in the disturbance to the process, and the disturbance has to be rejected. Okay. Now, one thing I need to reinforce: when you have only proportional controller, whether it is a servo problem, tracking problem, or a disturbance rejection problem, you'll always have an offset. Okay. So in the previous case, what would be the offset? Looking at that result. I'm not really then getting through, am I? Does everybody get that? Okay. So what is the offset? How do you answer that question? The offset is the difference between the final steady state value and what you want it to be. So we wanted it to be 5. We are making a step change of 5. So we want the final temperature to be 5 degrees above the current steady state value, because these are all in terms of deviation variables. Okay? So we want it to be 5 degrees above, but as t goes to infinity, this term goes to 0. Okay? So the steady state temperature that you're going to get, the offset you're getting, the deviation you're going to get is only 1.18. You want it to go to 5, it goes only to 1.18. So there is an offset. Okay? And that offset, that number will be affected by changing Kc. Okay? And so the question might be, plot how does Kc change as you change how does offset change as you change Kc? Okay? So no matter whether it is a disturbance rejection or a servo problem, tracking problem, you will always have the offset if you have only proportional controller. So the next problem we are going to see how we can overcome that using the integral 1. But before that, let's look at a case where TR, the set point change is 0. So I want the process to remain at 0 in terms of deviation variable, meaning it must remain at the current steady state value, whatever it is. But there is a disturbance coming in from the inlet temperature to the tank. It goes up by 5 degrees. What should you do? Okay. So of course, when that happens, you will sense that, and then you'll go back and adjust your heating rate. You'll adjust your heating rate in such a way that temperature is brought back. And how fast will you adjust? That is what you're going to decide as a control engineer. You're going to decide what should be the Kc value to determine how fast the response is. Okay? How would you begin? to answer that particular problem. A 5-degree step change in this, and plot the dynamic response of the effective process under a feedback control system where Kc is equal to 5, 10, 20, 100, etc. A series of numbers. Find the effective transfer function. If you're doing it by hand, you will find out what is T prime divided by Ti prime. Okay? Because you're making the change to Ti, so you want the effective transfer function between those two. So what would that be? Using the rule, whatever is in the forward path between the output and the input divided by the loop. Okay? So in this case, there is only 1 over tau s plus 1, that is between the forward path between Ti and T prime, divided by 1 plus everything in that loop. Okay? So that's going to be GCA divided by tau s plus 1. That is going to be the effective transfer function. Now we can plug in the numbers and then put Ti prime as equal to 5 divided by S, a step change. Okay? Of course, you should be able to do the same thing if I have not a step change but an impulse. Okay? Impulse response, you should be able, what would be the thing for impulse response? It is 5. Okay? And if it is a sinusoidal change, if I give you the amplitude and frequency. So this is why we saw all these in parts. Now we should be able to put it together in one of any variety of number of ways, Simulink, MATLAB, or by hand. Okay? And there it is. So this is the effective transfer function, T prime over Ti prime. And we'll rearrange, simplify, and get it as an effective gain and an effective time constant. Now, this time constant is different from the process time constant. Tau is the process time constant. Okay, whereas this tau 1 includes the effect of the feedback controller. It includes, for example, Kc. Okay? So in fact, I've given you what tau 1 is. Tau 1 is equal to tau divided by 1 plus Kc A. Okay? So it depends on both the heater transfer function A and the controller transfer function Kc. Now, at this stage, if I ask you to find out what is the offset for this kind of a regulatory problem, how would you go about it? There are many ways of doing it. One is, okay, I have the effective transfer function, I can invert it, I get the time domain solution, and then look at time as t goes to infinity. Another quicker way is to use the final value theorem without even having to go back to time domain. You can say, okay, I know the transfer function, so if I multiply it by s and take the limit of s going to 0, I'm going to get the final value without having to solve the problem. And so when I do that, I get the final value of the process temperature as t goes to infinity is as s goes to 0, s times Ts. Okay? And then multiply by s, and so I think there should have been I have a typo here. Can you find out what the typo is? I didn't multiply by s there. Here I did. The next one, that s should be there, and then this entire thing is A2 divided by tau 1 s plus 1 multiplied by 1 over s. Okay? So this is for a unit step change. For a unit step change. Okay? So then the s will cancel out, and when you put s equals 0, you get A2. So A2 is your final temperature. So the offset will be the difference between what you want it to be. In this case, you want it to be 0 because it's a disturbance rejection. So you want the final process temperature to remain at 0 deviation variable. That is, whatever the current value is, you want it to remain there. Minus whatever this particular controller does. And it takes it to 1 over 1 plus Kc8. So that is an analytical expression for the offset. Okay, so we can do this now for various values of Kc. What do you see? As you increase Kc, what happens to the offset? It gets smaller and smaller. So the only way to get rid of the offset is to have Kc is equal to infinity. Okay? But there are other consequences of increasing Kc. Large value of Kc will give you a very quick response, very dynamic response, but it might make the system unstable. So that we will see how to understand the implication of changing KC on stability, and how do we design it in such a way that the feedback control system remains stable. Any questions? Okay, here is a specific numerical problem. Okay, determine the closed loop response for the proportional gain of Kc equals 5, 10, 20, and 100 for a disturbance of 5 degrees. Determine offset in each case. Do this with Simulink, then get the response and time the mean by hand. Okay, so there is the Simulink block diagram. How many of you feel that you still need help in Simulink doing this? If I give you this problem and put you in front of a computer, how many of you will have difficulty building the block? The reason I'm asking is I need to then give you some more problems and assignments that you can do. We've done this enough that all it needs is practice. I don't want to construct in front of you every time because that takes up time. Right? So is it okay if I just throw this diagram and then go through it? Or, okay. Good question. I just copied from the earlier one and added what I needed, but if I didn't do something to the step change, I will be introducing an error. So let me actually start. That's only that copy of the diagram. Here I have the actual Simulink model. So your question is, why do I have this? Right? Now look at and tell me, does it matter? I've gone into this program and changed it to 0. There is no step change. Okay, it's still there so that in case I want to replace it with something else, I can do that. But that step change is not effective. But what I've done from the previous problem is added this block. Okay, this is the step change that corresponds to disturbance rejection. So here I have a disturbance of 5 units in Ci. Okay, and that enters just before the process. Okay, so the process is here, 1 over 5s plus 1, and this is the disturbance that is added to whatever the signal that comes from the heater. Okay, and then this is a measurement. The measurement block is 1, and this is the feedback control, feedback loop that goes back. So it's essentially the same thing that I had before for the first problem that we did. All I've done is I've added a step change. So this is where the power of Simulink is. So if you have this, I can then ask you questions like, what would happen if I put a sinusoidal change? What would happen to the output frequency? What would happen to the output amplitude? And that is an important part because when you're doing the stability using something called the Nyquist method, we will be using this kind of an analysis. But for now, let's get back to this. So I have left Kc as a symbol here. This is the controller gain. And this is the heater, 1 over WC, 1 over 14, which is 0.0714. And you should be able to change any one of them to appropriate process model. And so in order to run this, all I need to do is, in the workspace, I need to define Kc. Okay? So I go back to my workspace and put Kc as equal to 5. Because I want to do this as a parametric study for Kc equal to 5, 20, etc., I'm just building myself that freedom by simply defining Kc as a symbol here. If I open the block, all I will have is gain as simply Kc, a symbol. So when it executes it, it's going to look into the workspace to look for that value. Now I can execute that. And you can see that figure. Okay, can you interpret that figure? What would the yellow line is the dynamic response when Kc equals to 5. What would you ideally like that to be? 0. So even though it goes up, you want it to come back there. And a purely proportional controller is not able to do that. Okay. So what is the offset in this case? On this diagram? Something like that, yeah. So it's the difference between the yellow line and the purple line that you will see at the bottom. So the purple line that you see, let's close this, that's not working. The purple line that you see here is the set point. So set point hasn't changed for the regulatory problem. Just a disturbance, and the disturbance has to be gotten rid of, and it's not able to do that. But we know that as we increase Kc, it will be able to do that. Okay, so go back to the nodes. Now we want to do this, run this simulator, the Simulink model, many times, going from Kc equal to 5 to 100. Okay, so here I've set up a loop. We're going from 5 to 100 steps of 5. Each one is a value of Kc. Okay, because I've built Kc as a symbol in the Simulink, I'll be able to run this from MATLAB. So all I'm doing here is setting up a loop for every value of Kc in that vector Z that I created, and then I pick that value from the vector Z, store it in Kc. Now it is this one that is going to pass the value of Kc to Simulink. So here I'm defining the value of Kc every time as I go through this loop. The loop is repeated 20 times or 19 times or whatever. And this is the one that actually executes the Simulink model. So the command is sim, and this is the file that contains the Simulink model. So you build a Simulink model, save it in a file, and then give the file name here. Here you say do it till 15 minutes. That's the time over which you want to integrate the Simulink model. And then what Simulink sends out is a vector called t, which is a time, and a vector called x. This I think I probably did not answer last time to your question. X is actually something called a state variable. For now, we will not worry about what it is. When we look at state space models, we will understand what it is. But Simulink automatically deals with an internal variable called a state variable, state space variable. That's what X is. Now, Y is the variable that we compute in the Simulink model. So if you go and look at the Simulink model, I send out two values, out 1 and out 2. Okay, so these are the ones that are sent out as Y in the command where I call the Simulink. Okay. So Y contains all the output links. I can have as many output links as I want, but it will be sent as columns of Y. So Y will be actually a matrix. Each column will contain one of those output links that I have in the Simulink block. So in this particular case, let me ask you a question. What would out 1 and out 2 contain? We're looking at this. This is 2 here, and that is 1. So what should the first column of Y be? What should be the second column of Y be? The process temperature response, and the second one is the 0, what I want it to be. So the difference is the offset that I want to calculate. I want to calculate the offset. So I'm sampling what is the temperature that I want it to be in 2, that is the second column of Y, and I'm sampling what is the actual process temperature in the variable 1, which is the first column of Y. Okay? And that, if you understand that, what Y contains, then you will know what I'm doing in the next few lines. Here I'm simply plotting T versus Y, and here I am finding the number of entries in the vector Y. Why do I need to do that? Here I'm saying integrate up to T equal to 15 minutes, right? But I don't know what time step Simulink took. Okay, so I don't know how many entries it would have in the column vector Y. Okay, so to find out how many entries I have, this function size tells me how many rows and how many columns are there in Y. Then I can say pick the last row. That's what I'm doing here. Last row from the second column minus the last row in the first column. Because the last row would be my steady state, hopefully. When could that go wrong? If it takes a very long time and 15 minutes is not adequate enough, okay, then that offset calculation would be wrong. So you need to make sure, this is why I plot it. I plot it to make sure that they have leveled out. Then, if it's not, then I have to come back and change this number from 15 to 30 or 200, whatever it is. Yeah. Yeah, the sign tells you in relation to what you want where the temperature is. Okay, whether it is above that or below that. Where are you talking about this programming here or in the plot? Yeah, you see that. Yeah, that depends on the definition of the offset, right? So if you look at the analytical part, if I define offset is defined as TR infinity minus T infinity. Okay. So TR infinity is 0 and T infinity is 1 over 1 plus KCA. So the offset is going to be negative. The graph is going to be yeah, it will be, and that's what. See, here is the response. I will actually run the program. You will see. So this is the response for all those 20 values starting from Kc equal to 5. So the offset here is this value, but with a negative sign. Okay, and the offset for Kc equal to 100 is this, but with a negative value. So when I plot the offset alone, I think that's what you're asking. It should be a negative value, right? So it goes from minus 3.5 when Kc equal to 5 all the way down to minus 0.5 when Kc equal to 100. So the offset decreases, right? Because that's the way that we define the offset. You can define the offset as Ti minus Tr, okay? I mean T prime minus Tr prime. So it's a departure from the required steady state value, and that departure keeps going down. So that is the departure that keeps going down. Okay. Is that, am I getting the which graph are you talking about? The previous one. Oh, yeah. This simply says, let's make sure that we understand this, okay? I don't want to sidestep this. What does this diagram tell us? This diagram tells us whatever the steady state value is, okay, the process temperature is going to be above that. So when Kc is 100, for example, the steady state temperature is going to be 0.5 or 0.6 degrees above what we would like it to be. Suppose the process is operating under steady condition, it's 80 degrees, outer temperature is 80 degrees, okay? And the inlet step change is 5 degrees, the inlet temperature. So the controller is going to take action by reducing the heating rate to get rid of that 5 degree effect, the effect of 5 degree increase in the inlet temperature. But it's not able to do that. So all it's able to do is, instead of bringing it from, without any controller action, what would happen to the outlet temperature? If the inlet temperature goes up by 5 degrees, it's a linear process, the outlet temperature will go up by 5 degrees over a long term. So the controller action is bringing it down to, instead of 5 degrees, if it is 80 degrees, instead of being 85, it's going to be 80.5 when you use Kc equal to 100. So this diagram simply tells you what will be the process temperature, and if you are asked what is the actual process temperature, you should know what is the current operating steady state value is, add this to that, and that will give you the process temperature. Okay? But the offset is defined as the deviation from this. Okay? And so that offset decreases as Kc increases, but it is a negative value simply because that's the way we defined it. Okay? And yeah, so the definition says 0 minus that. Okay, and that's why I get that negative sign there. Any other questions? Yeah. Yeah, let me just run this. Okay, so this is the script file. So you're asking this one, right? Is it plotting both columns or one? Yeah. That is yeah, you do see another line, but and now as you run through this loop, you will see that it keeps on adding to that graph. At the same time, accumulating what the offset is in line 9, but it doesn't plot it. It accumulates the offset for every value of Kc, and then it'll plot Kc versus the offset at the end. So you see the second line appearing, third line appearing. So every time I go through the loop, now if you want to look at the value of Kc currently, it's 20. Okay, so it is just keep on plotting that. Remove this and then run it. It's going to add all the cases and then plot the final graph, which is offset versus Kc. Okay. That's the last line. Line 13 generates this graph. Pretty true. Any questions? Yeah. Yeah, good question. So you're asking, when I have a disturbance, simultaneously I have a step change in the goal. Is that what you're asking? What do you want the goal to be? 5 or minus 5? Let's do it 5. I don't know the answer. To find it analytically is going to be very complicated. You have to use superposition, a lot of algebraic manipulation. Because you can always, this is now what we are doing is, we have step change in both the disturbance and in the regulatory problem. Okay? So when you run this, so the step change, wow, it looks like it reached, there was no offset. I was not anticipating this. I thought that there will always be an offset. So there must be a special situation where the controller, like if you make a disturbance change of 5 degrees, the heater is trying to compensate that, right? So that somehow cancels. Yeah. Right. Disturbance of 4 you want, right? Okay. This is the nice thing about MATLAB Simulink environment. See, now you have an offset. Right? So that was a special cancellation because it was 5 in both. But you do have an offset, yeah. And you can play with this by putting inputs in the input or sinusoidal or any other. Remember, in one of the exams, you had this complicated input function. We had a ramp and then a step and then things like that. So Simulink makes all those very easy to implement. Any other questions? Okay. All right, here by hand. Okay, by hand simply means you're going to find this effective transfer function between the output and the disturbance in this case. And I've shown you, after plugging in all the numbers, what happens to that effective transfer function. Okay? That is going to depend on Kc. Okay, so you have to do this for every Kc by hand. And then you can put a step change for Ti, that is 5 over S, step change of 5 units, and then do the inverse in MATLAB, and you get your time domain solution like this. And once again, if I ask you the question, what is the offset here? The offset you need to find out as t goes to infinity, because of this negative sign, this goes to 0. and this is your final steady state value. But we want it to be 0. So the 0 minus this is your offset, which will give you the negative 3.684 or a KC value of 5. Okay. Okay, let's start up the next problem, which is proportional integral control. Okay. So the same problem, the same heating system, but GC now is going to be handled by this transfer function, KC plus 1 over tau IS, an integral time constant. Okay. Everything else remains the same. Okay. So what does it do to the response? Now the integral action we have seen already is one that accumulates errors. The purpose of the integral action, integral is area under the curve. So if you have an error that is coming from here, the error is a function of time. The error persists. The integral action is going to accumulate all those errors and take an action in proportion to that. And that's why it's able to drive the error down to 0, because it's not just looking at the current error, but it is looking at all the past error and accumulating it. Okay, and that is the integral, the Laplace transform. The integral is 1 over s. Derivative is always multiplication by s. Integral is division by s. Okay, that's why you get 1 over s from there. Okay, so now the only change from the previous part is change in GC. Okay, so that GC that we had previously for the effective transfer function is going to be replaced by Kc times 1 plus 1 over tau IS. But look what it does to the effective transfer function. If you have to simplify this, by simply looking at it, can you tell is it going to be first order, second order, or unpredictable? It turns out to be a second order. Okay? So you need to do an algebraic manipulation. For example, take the common factor, tau s plus 1, and multiply this out. Okay? And you will get, this is equal to 1 divided by tau s plus 1 divided by tau s plus 1 plus Kc times 1 plus 1 over tau IS times A divided by tau s plus 1. Okay, so this tau s plus 1 cancels with that, and what you get is 1 divided by, oops, I've given you only the final result there, 1 divided by tau s plus 1 plus Kc times 1 plus 1 over tau IS. So you need to multiply again by tau IS. Okay? And so you'll get the tau IS in the numerator here, and in the denominator it goes to s squared. And tau I and tau get multiplied. So the time constant now is process time constant till is tau. Okay? But the effective time constant for the process now changes because it changes into a second order process. Like immediately what should come to your mind? Second order process can have oscillatory response. Critically damped, over damped, under damped, all those possibilities exist. Even though the process is only a first order process. The heat and tank problem is a first order process, the integral action gives rise to an effective second order response. Any previous page? Yeah. Okay. Both at the same time. Okay. So if you want me to fill out an intermediate step, it will be tau IS, because now I'm going to take this and multiply everything by tau IS. So I will get tau IS times tau S plus 1 plus Kc times tau IS plus 1 times A. Okay? And then you need to expand that, and that's how you will get tau I times tau times S squared. And then collect all the S terms, you'll get these two, and then the constant term, which is Kc times A. Do I have an error there? Here I'm multiplying by tau IS, right? So it is, yeah, it is Kc, right? Thank you. And that's what gives you this term. Okay, you can, of course, do all this in MATLAB, and I've given you the code to do that. So here all I'm doing is I'm defining the process transfer function, the controller transfer function, and then the effective transfer function by applying the rule, forward divided by the loop. And then ask it to simplify it, so you don't have to do any of the algebra, and it simplifies and gives you this expression, which is the same as this one. And then you can do iLaplace to invert back. Okay? But the important thing to notice is that it makes it into a second order process. We're out of time. So we will look at the dynamic response of this in the next class. Okay. Have your pen.